Hello, so in today's lesson, our learning target is I can graph absolute value functions. So if you recall, in our last lesson, we did an introduction to graphing absolute value functions, and we also went over how to shift absolute value functions both horizontally and vertically, so side to side and up and down. So today, we're going to go a little bit further, and we're going to look at slope changes, negative flips, as we call them, and then combinations of lots of different sorts of transformations. So far, again, we've done lots of horizontal and vertical transformations, so now we know how to shift the absolute value function anywhere we want on the coordinate plane. But just like linear functions, how we played around with changing their slopes and making them positive and negative, we can do the same thing to absolute value functions. So first, we're going to look at slope changes. So let's start out with an example. Suppose we have f of x is equal to 3 times the absolute value of x. So we're going to graph it the long way using a table of values to start out. So I'm going to make my table. We're going to go from -3 to +3. And if f of -3 is going to be equal to 3 times the absolute value of -3, absolute value of -3 is equal to 3. So you get 3 times 3, which is equal to 9. F of -2 is going to be 3 times the absolute value of -2, which is equal to 3 times 2, which is equal to 6. F of -1 is going to be equal to 3 times the absolute value of -1, which is 3. F of 0 is just going to be equal to 0. And then we're going to start going back up again. So f of 1 is 3 times 1, which is 3. F of 2 is 3 times the absolute value of 2, which is 6. And f of 3 is going to be equal to 9. So if we plot these points, first one we're going to go left 3, and we're going to go up 9. I didn't make enough grids on this graph, but that's okay. Second one, we're going to go left 2, up 6. Third one, left 1, up 3. Then we have the point 0, 0. We have 1, 3, 2, 6. And then again, our graph's going to go up like that. And if we connect the dots, we get a classic V-shaped function, except this time it's just a little bit narrower than the ones we were looking at before. And that's because if we look at the left side, for each 1 unit we go right, we go down 3, which if you recall, that means it has a slope of -3 to the left of our vertex, whereas to our right, for each unit we go right, we go up 3, so that would mean we have a slope of +3. And you notice we still have all the classic defining characteristics of our absolute value function. We have the vertex, we have the V-shape, but the slope is just a little bit steeper, first in the negative direction and then in the positive direction. So what we realize is that for slope changes, the coefficient, this number in front of the absolute value function, represents the slope. And since we're looking at absolute value functions that go down and then up, the slope is -3 and then positive 3. Because all absolute value functions will have two different slopes for different parts of the graph. So now that we know this rule, just like with the horizontal and vertical shifts, we can very easily graph other slope changes. So I'll write this one in black. If we have f of x is equal to 1/2 times the absolute value of x, that means that to the right of the vertex, we're going to be going 2 right and up 1. And to the left, we're going to be going, for each 2 units we go right, we're going to go down 1. So we will get a graph that looks like this. And we could graph any slope we want on this. And so if we have the slope of a fraction, it's going to be a wider v. And if we have a bigger slope, it's going to be a narrower v, like that. So that covers the start of slope changes. Now suppose we have f of x is equal to negative times the absolute value of x. So in this case, if we do our handy table of values, f of negative 3 is going to be equal to negative times the absolute value of negative 3, which is equal to negative times 3, which is negative 3. Similarly, f of negative 2 is equal to negative times the absolute value of negative 2, is equal to negative 2. F of negative 1 is going to be equal to negative 1. F of 0 is going to be 0. F of 1 is equal to negative times the absolute value of 1, which is equal to negative 1. Then we get negative 2 and negative 3. So if we graph this function, we're going to get something that looks like this. And now we notice, hey, one, our graph is now an upside down V shape. And number 2 is that our graph is only in the negative y values, whereas before we were looking at graphs that were only in the positive y values. So this might worry us at first, because remember, we talked about how the absolute value has to be positive. But the reason that this graph is always negative is this negative sign out front. Because we know that this is always positive. We also know that when we multiply a negative number by a positive number, we always get a negative number. So that explains why we have these negative y values. And again, this time, on the left side of the vertex, the slope is positive 1, and on the right side, the slope is negative 1. So that represents a negative flip of the graph. And we can also have a negative flip with a slope change. So for example, if we wanted to graph f of x is equal to negative 2 absolute value of x, that would just mean that our slope to the left is going to be positive 2. So we're going to get this line. And to the right is going to be negative 2. So we'll get a line that looks like that. And again, we can do any negative slope change we want. So that covers both slope changes and negative flips. So next, we're going to start looking at combinations of different types of transformations. So I'm going to move this whiteboard over here. And the key to doing combination transformations is just to look at them and take them one step at a time. So suppose we have f of x is equal to say 2 times the absolute value of x minus 1 plus 3. Let's make a table of values for this one, although it will be a little bit tedious. So if we go from negative 3 to positive 3, we will notice that f of negative 3 is equal to 2 times negative 3 minus 1 plus 3. Absolute value of negative 3 minus 1 is absolute value of negative 4. So we get 2 times 4 plus 3, which is equal to 8 plus 3, which is equal to 11. So now f of negative 2 is going to be equal to 2 times negative 2 minus 1 in the absolute value plus 3, which equals to 2 times 3 plus 3, which is equal to 6 plus 3, which is equal to 9. F of negative 1 is going to be equal to 2 times negative 2 plus 3, which is equal to 7. F of 0, this x will go away, so we'll just get 2 plus 3, which is 5. F of 1 is going to be equal to 3. F of 2, we have a 2 times 1 here, so this is a 1. 2 times 1 plus 3 is equal to 5. And then f of 3 is going to be equal to 2 times 2, which is 4, plus 3, which is 7. So we notice this pattern where this is going to be our vertex, because that's the turning point of the graph. So we have the point negative 3, 11, which is way up here. We have negative 2, 9, which again is way up there. We have negative 1, 7, which finally we can plot up here. We have 0, and then we have 5, 0, 5. Then we have 1, 3. And then we start going up again. So we get 2, 5, and then we get 3, 7. So our graph is going to look like this. So now let's examine or analyze the characteristics of this graph. So we have a rightward shift of 1. So we go right 1. We went up 3. And then we have a slope of 2 on this side and negative 2 on the other side. So if we look at our original function, we have plus 3, which means we're going up 3. We have minus 1, which means we're going right 1. And we have a slope of 2. So essentially, we could have avoided the annoyingness of making this table of values and doing all these calculations by just starting at the origin, going up 3, right 1, and changing the slope. So now let's do an example using the quick and easy method. So we'll say f of x is equal to 1/3 times x plus 3 minus 4. So we're going to go down 4. So if we start at the origin, we're going to go down 4. Then we're going to go left 3. So 1, 2, 3. And this is where our vertex is going to be. And then we have a slope of 1/3, which means it's going to look like that. So again, that was so much easier than going through this whole table of values. It was just taking it one transformation at a time. And I just wanted to do one last example of a really, really complicated one. So let's say f of x is equal to negative 4 times the absolute value of x plus 2 plus 6. So again, we're going to start at the origin, and we're going to go up 6. So up 6. Then x plus 2 in the absolute value signs means that we're going to go left 2 units. So 1, 2. So that's going to be where our vertex is. And then if our slope is negative 4, that means that our graph is going to look like this. Which make that neater. Which again, you notice, we're up 6, left 2, slope of positive 4, and then negative 4. So whenever you have a negative in front of the absolute value, instead of the V, forward V shape, we're going to have an upside down V shape. So I guess that concludes our lesson on graphing transformations of the absolute value function. In our next lesson, we're going to go over how to find the domain and range of these functions. So stay tuned for that.